This comes out of section 8.6, logarithmic differentiation. Just before we start, I just want to make sure everybody remembers that if you have y equals ln x, that the derivative is 1 over x. But it's also true that if you have y equals ln the absolute value of x, that the derivative is 1 over x. And we showed that using two cases of x is greater than 0, of x is less than 0. But so what we do, if we have something like this function, for example, we have a pretty complicated function. We would be using, the quotient rule, chain rule, product rule, the whole assortment again. So let's try this using logarithmic differentiation. This one is slightly different than the last example in that this cube root function that I have here actually does have the potential to be negative. And so if I try taking the natural log of both sides, I should just put an absolute value symbol around it to say, well, I'll make sure I'm not logging any negative numbers by putting an absolute value sign around all this. Now, when I take the derivative, it really doesn't make a difference anyway, because the derivative, as you see up above, of absolute value of x is still just 1 over x. But it can end up making a small difference in your answer, depending on what your function is. But so we still will pull this apart as using log rules. So I could put everything to the power of a third instead of having a cube root there. So I'd x to 2/3 times sine x in brackets to the 1/3 over x cubed minus 1 to the 1/3. The reason why it's worth doing that is I can now say ln y equals ln of x to the 2/3 plus the natural log of sine x to the 1/3 minus the natural log of x cubed minus 1 to the 1/3. And notice I'm being as careful as I can with these absolute value signs. It turns out in this example it won't make a big difference anyway, but the last thing I can do before I take the derivative here is I can still bring out these powers here, say, well, ln x here times 2/3 plus 1/3 ln sine x, and then minus 1/3 ln of x cubed minus 1. Now I take the derivative of everything. I've got 1 over y times y prime, or y prime over y equals 2/3 times 1 over x plus 1/3 times 1 over sine x times the derivative of sine x, which is cos x, minus 1/3 times 1 over x cubed minus 1 times the derivative of that. Now, all those absolute values went away anyway. In this case, I'll show you in a later example why you want to be a bit careful about that. And so y prime equals y times all of that. So y times 2 over 3x plus, maybe it's worth saying a third cotangent x, or cotangent x over 3, and then minus the 1/3 and the 3 cancel out, so x squared over x cubed minus 1. And finally, I could say, well, y was that beginning function that I had, the cube root of this mess here. And so if I need to write everything in terms of x, I can say, well, it's this times what I just had in the brackets, 2 over 3x plus cotangent x over 3 minus x squared over x cubed minus 1. And no one piece of that was especially hard. It was a bunch of steps because I had to use my log rules and stuff, but the actual differentiation step was made quite easy instead of having product, quotient, chain rule all blended together in a great big adventure. And if somebody gave me, x equals pi over 6 and said, what's the slope of the tangent line on this graph, we could put pi over 6 in there and figure it out.